Bismillahirrahmanirrahim. Assalamu alaikum, brothers and sisters. In today's problem, we apply the Fermi-Dirac distribution function to describe the energy states of electrons in metals, which can give us a lot of insights into their electrical and magnetic properties. The electron contributions to heat, capacities, and other behaviors. So just stick around for more details. Watch and learn. The problem is silver contains 5.8 times 10 raised to the 28 free electrons per cubic meter. At absolute zero, what are, letter A, the Fermi energy in joules and electron volts of silver? Letter B, the speed of an electron with this energy. And C, the density of states in states per joule and states per electron volt of the Fermi energy for a block of silver of volume 1.0 cubic centimeters. In our free electron model of conductors or metals, the electrons are treated as completely free particles within the conductor. And we describe a box with side length capital L illustrated in figure 1. The energy levels for a particle in this box are given by equation 3 below. We are given the electron concentration, small letter n, equal to 5.8 times 10 raised to the 28 electrons or free electrons per meter cube. As described in figure 2, the allowed values for nx and y and nc are positive integers for the electron states in the free electron gas model. Including spin, there are 2 states for each unit volume in space. The volume of the silver metal is also given, equal to capital B equals 1.0 centimeter cube, or that is 1.0 times 10 raised to the negative 6 meter cube. The given absolute temperature, capital T, is 0 Kelvin. And our target variables are, in part A, the final or the Fermi energy, capital E, sub F naught of silver expressed in joules and in electron volts. In part B, the Fermi speed of the electron, small v, sub F. And in part C, the density of states expressed in states per joule and states per electron volts of the Fermi energy for a block of silver of volume 1.0 cubic centimeters. We denote it as small g as a function of energy, capital E. Figure 3 shows the graphs of the Fermi-Dirac distribution function for various values of small k times capital T, or the Boltzmann constant times the absolute temperature capital T. Notice that uh, as temperature capital T increases, more and more of the electrons are excited to states with energy capital E greater than uh, capital E sub F, right? And based on the Fermi-Dirac distribution function, we can actually find the probability, right? The probability that a given state is occupied by an electron. And this is given by equation number 1. So the Fermi-Dirac distribution in terms of the probability of finding an electron in a given state is given as uh, small f quantity capital E equals 1 over, or the reciprocal of, the Euler's number raised to the power capital E minus capital E sub f over small k times the absolute temperature capital T plus 1, where in this equation capital E refers to the energy of state, while capital E sub f is the so-called Fermi energy, right? So if we are referring to the Fermi energy at absolute zero, the symbol becomes capital E sub f naught. Small k, of course, is the Boltzmann constant, and capital T is the absolute temperature. We can accurately let capital E sub f equal to capital E sub f naught for metals, because the Fermi energy does not change much with temperature for solid conductors such as uh, metals. However, it is not safe to assume that capital E sub f equals capital E sub f naught for semiconductors, in which case the Fermi energy usually does change with temperature. Given in equation 2 is the electron concentration, small n, equal to the total number of electrons, capital N, per unit volume, capital V. And we set capital E to the Fermi energy at absolute zero, capital E sub F naught. So in this equation, small m refers to the mass of the electron, and of course, h bar is the reduced Planck's constant, or Planck's constant divided by 2 pi. So, moving on to our computations for uh, the first target variable in part A, the energy, capital E sub F naught, using equation number 3, equal to the square of the reduced Planck's constant divided by twice the mass of the electron, then multiplied by bracket 3 times the square of pi times the value of small n, and then all quantities inside the bracket will be raised to the power 2 over 3, which means raised to the second power, and then we get the cube root. That is, when we substitute, we have capital E sub F naught equals 1.055 times 10 raised to the negative 34 joules second, then squared. That is the value of h bar, or the reduced Planck's constant. Then divided by twice the mass of the electron, 9.11 times 10 raised to the negative 31 kilogram. Okay, so whatever is their quotient, that will still have to be multiplied to the result of getting the value of 3 times 9.87, the square of the pi value, multiplied by the value of small n, 5.8 times 10 raised to the 28 free electrons per meter cube, then raised to the power 2/3. When we do our math, we get the value of the energy, uh, capital E sub F naught equal to 8.7 times 10 raised to the negative 19 joules, which when converted to electron volts is also the same as 5.4 electron volts into significant figures. Room temperature of 20 degrees Celsius, which is, of course, equal to 293 Kelvin, uh, we compute the product of small k and the absolute temperature, capital T. That is 1.381 times 10 raised to the negative 23 joules per Kelvin. That's the value of the Boltzmann's constant, times 293 Kelvin. And we get the value of small k times capital T equal to 4.04 times 10 raised to the negative 21 joules, which is also equal to 0.0254 electron volts. And here we see that the calculated Fermi energy is much larger than the product of small k times capital T at ordinary temperatures. So it is a good approximation to take almost all the states below capital E sub F as completely full, and almost all those above capital E sub F as completely empty. And in part B, we use the non-relativistic equation to find the speed small b sub f, or the electron speed small b sub f, okay, equal to the square root of twice the energy capital E sub f divided by the mass of the electron, expressed here as equation number 4. That is, the speed Bf equals the square root of 2 times 8.7 times 10 raised to the negative 19 joules, and then divided by the mass of the electron, 9.11 times 10 raised to the negative 31 kilogram. So when we do our math, we get the value of the electron speed equal to 1.4 times 10 raised to the 6th power meters per second in two significant figures. That is, the pre-electron speed here, okay, is of course way below the speed of light in vacuum. So this justifies our choice for the non-relativistic equation for determining the speed of the pre-electron. In part C, we apply equation number 5 to compute the density of states denoted here as small g uh, as a function of energy capital E. Okay, so the formula is g as a function of capital E equals uh, 2 times the mass of the electron raised to the power 3 halves and then multiplied by the given volume capital V divided by twice the square of the pi value multiplied by the cube of the reduced Planck's constant and multiplied by the energy capital E raised to the power 1 over 2. Substituting our quantities, we have uh, small g as a function of capital E or energy equals 2 times 9.11 times 10 raised to the negative 31 kilogram and raised to the power 3 over 2 multiplied by the volume capital B 1.0 times 10 raised to the negative 6 meter cube all over 19.74, which is twice the square value of pi, and then will be multiplied by the cube of uh, the reduced Planck's constant, 1.055 times 10 raised to the negative 34 joules second, and multiplied also by the value of the computed energy capital E raised to the power 1 over 2. When we do our math, okay, we find the density of state equal to 9.9 times 10 raised to the 40th power. That is states per joule, which when converted to electron volts or states per electron volt, we get the value 1.6 times 10 raised to the 22nd power states per electron volt. Both answers expressed in two significant figures. Just before we end, let us reiterate the key concept applied in this problem. The Fermi energy in the free electron model of a metal depends on the electron concentration small n, which is the number of electrons per unit volume. In a typical metal at room temperature capital T, the Fermi energy capital E sub F is much greater than the product of Boltzmann's constant and the absolute temperature capital T. So on these notes, let me say mabuhay. Till the next episode, MashaAllah. Thank you very much for your indulgence. Please don't forget to subscribe to my YouTube channel. Alhamdulillah.